Alright, Assalamu alaikum. So we've been talking about forces on conductors, and we've already seen that if we have a conductor that is carrying a current I in a particular direction, which is the direction of the conventional current, even though current is a scalar, and if we take a small section of this wire of length dl, then a force acts on this conductor if it's placed inside a magnetic field and if the disposition of the magnetic field is in the proper direction. For example, if the magnetic field that this current carrying conductor is immersed in is pointing out of the plane of the blackboard, then a force will act on this section and consequently on the entire wire, and the direction of this force will be given by the right hand rule. dl defines the direction of the current. idl is the current times the length of this section. So idl points to the right and b points out, so my thumb then points in the direction of the force. So idl crossed with the magnetic field b will give the differential force on the element that we've been talking about, df. So the force on this element df is going to point in the downward direction, and likewise there will be a force on each one of these sections. So this entire piece of wire will experience a magnetic force, and that magnetic force will be given by IL, where L is the total length of this piece of wire crossed with B. But this formalism not only holds true for current carrying conductors, it holds true for any current, any moving charges. Whenever there is net transport of charge, we have a force acting on the moving charge. And if we were to take a charge Q moving with a velocity V, then we know that the force acting on this moving charge will be FQV cross B. So this is just the Lorentz force. And we can use the vector rule product to find out the direction of these forces. So what I have here is a small demonstration for you. In this demonstration, Ali, please run on kar do. So primarily, let me first show you what the piece of equipment is. So what we have here is an oscilloscope. So this is an oscilloscope. I've taken out the cathode ray tube from the oscilloscope. So the entire high voltage circuit is inside this box, which is making the electrons come out by thermionic emission, and it applies the voltages to the vertical deflection plates. So the tube, however, has been taken out from this box, and now I also have a function generator here. The function generator can apply voltages of different kinds, sinusoidal, sawtooth, or triangular or square pulses to the vertical deflection plates. So what we have in an oscilloscope basically is, as you all would all know, we have a source of current, which is a source of electrons. We pass current through this filament. Electrons are ejected with a certain velocity, and they are pulled towards an anode, which is a high voltage point. So electrons are accelerated towards the anode. There is an aperture in this cathode. Electrons move towards the anode, and then you have vertical deflection plates. You apply a vertical voltage to these vertical deflection plates, and what this electric field would do is would move the electrons. The electrons would move under the action of the electric field. So the force on the electrons due to the electric field would be QE. We can also have horizontal deflection plates. So a horizontal voltage is applied, which means that the electric field that is applied is horizontal. The combined electric fields on the vertical and horizontal plates can displace the electron beam. Generally, a sawtooth voltage is applied to the horizontal plates so that the beam moves towards the left, then comes back, moves towards the left and then comes back, moves towards the left and then comes back. And eventually there's a screen here. So if you look at the screen from the top, the electron, if a horizontal voltage has been applied, is moving sideways. And if a vertical voltage is applied, the electron will move up, and if the vertical voltage applied is negative, the electron will move down. So you will see swings of electrons, which are traces of electrons on the computer screen. Now generally, inside this oscilloscope, we are only applying electric fields. Now what I would like to do is, I would like to impose on top of it a magnetic field. Ali, could you please focus on the screen now? Screen के ऊपर जरा ध्यान. Alright, so what you see on the screen is I've applied a square voltage on the vertical deflection plates and a sawtooth voltage on the horizontal plates. So you can see that the electron is moving sideways, laterally, from left to right. So in order to show you that I've indeed applied a sawtooth voltage or a square voltage, have a look at this. So I've applied a square voltage on the vertical deflection plates. This applies an electric field. The electron is going up, down, up, down, up, down. But it's also moving sideways because I have applied a sawtooth voltage, a laterally deflecting voltage on the horizontal plates. And this is a trace, this is a paintbrush view of the electron that falls on the screen. The screen then phosphoresces and gives out a color. So this is how we see electrons inside this cathode ray tube. So these moving electrons actually form a current, right? And the direction of the current is opposite to the direction of the velocity of the electrons, the conventional current. So what I'm going to do now, I'm going to take a piece of magnets and I'm going to bring these close to the cathode ray tube. So now the electrons are coming towards you, right? So if you look at the screen, the electrons are approaching towards you. That's the direction of the velocity of the electrons. Now I take this magnet here, right? This is a piece of magnet, and I'm going to move this magnet close to the electron gun in a direction like this, which means that the magnetic field will now be sideways. The electrons are coming towards you, the magnetic field is lateral. So the direction of the supposed magnetic field is perpendicular to the direction of the velocity of the electron. And let's see what happens. I'm moving these magnets close to the cathode ray tube, and you can already see that these electrons are actually moving upwards. They are being deflected by the magnetic field. Okay, let me just so I have two magnets, and I bring these magnets close to the cathode ray tube, and the beam reflects upwards. All right? In fact, they start taking up a spiral path. They start taking a circular path. Now change the orientation of the magnets, which means that instead of a north pole facing the cathode ray tube, now I have a south pole facing the cathode ray tube. And now you will see that the electrons are deflected in the opposite direction. So now what we have in this case is a combined electric and magnetic field that is being applied to the electrons. In fact, if I move the magnet such that it is now normal to the electrons, which means it's parallel to the axis of the electrons. I hardly see any motion of the cathode ray of the cathode rays trace. Now I move this perpendicularly to the direction of the electrons. The effect is large, and this bending of the electron trajectories. So these electrons are indeed being affected by a magnetic field. Now I can get all kinds of pretty patterns, in fact, on this oscilloscope. So if I have this kind of trace, I've applied a sinusoidal voltage to the so I just move the vertical bias so that I get this in the middle of the screen. Well, and now I apply a magnetic field on both sides of the cathode ray tube. So you'll see that I can get all kinds of pretty patterns, in fact. This trace can be deflected on all kinds of directions depending upon the direction of the magnetic field. So these electrons are indeed being deflected by magnetic fields. And in fact, you can do a mathematical analysis of what the trace should look like if the magnetic field is pointing in all kinds of weird directions. So now I'm going to change the orientation slightly. All kinds of patterns can be produced on the. Look at this pattern. Look at this pattern. Okay? So one can do, in fact, a proper mathematical analysis of the combined electric and magnetic fields, provided you know what the direction and the magnitude of the magnetic field is due to these bar magnets. Okay, so all kinds of pretty patterns, Lissajous figures, all kinds of weird things can be actually seen. Now I have the magnetic field pointing into perpendicular direction, so there is a net vector magnetic field pointing in a diagonal direction. This causes a diagonal shifting of the cathode ray oscilloscope trace. Let me apply this square voltage back again. Look at the pattern now. So all kinds of beam steering can be done with the help of magnetic fields. Apply sawtooth voltages. So this is in fact a nice student project of finding out these patterns from first principles, from finding out these patterns from the Lorentz force that acts on these electrons. Okay. I'm going to change the orientation of one of the magnets. The trace has in fact gone off screen. I can stretch, I can expand the sawtooth voltage can start breathing. Okay? So all kinds of pretty effects can actually be seen, which actually shows that these electrons, which are currents, nothing but moving charges, can in fact be deflected by magnetic fields. Thank you, Eddie. Now I would like to move on, and the concept that I would like to talk about is what happens when actually charges move inside magnetic fields. Now suppose Now this is my defining equation, the Lorentz force, and if I have combined electric and magnetic fields, the total force will be given by QE plus QV crossed with B. Right? In the meantime, could you circulate in attendance, please? Now let's draw a diagram of what's going to happen if I have a positively charged particle of charge Q that is moving rightwards with the velocity V. And all of this is placed inside a magnetic field. And the magnetic field is disposed normally to the direction of the velocity. So the field is pointing outwards. Now what's going to happen? A force acts on this moving particle. What's the direction of this force? Yeah. Upward. V crossed with B is downward. Alright? So the force is going to act downward. Now this is a velocity, and associated with this velocity is a momentum, mv. If this velocity is really much smaller than the speed of light, if the velocity approaches the speed of light or is really large, then this p is in fact given by gamma mv, where gamma is defined as 1 over 1 minus v squared over c squared under root. This is a relativistic factor, a relativistic correction. Note that if v is really smaller than c, then this thing turns out to be equal to 1. However, if v approaches c, then gamma increases. Alright, so this comes out from special relativity. You've seen this in modern physics, I suppose. So now this is the momentum of the particle, and a force acts on this particle. The direction of this force is downward, F. Now what is a force? A force is actually the rate of change of momentum. Now this is the initial direction of the momentum. What this force is going to do, it's going to bring the momentum vector downwards. It's going to change the velocity's direction. So now there will be a shift in the velocity or a shift in the momentum, and the direction of this change in momentum is going to be downwards. Delta P, the change in momentum, is going to be downward. It's going to be parallel to the force. So what this delta P is going to do, you have an initial momentum P, and you have a change in momentum delta P, you will get a new momentum. That new momentum vector is going to point in a different direction from the original P. So this is our new momentum, which is also the direction of the new velocity. So what's going to happen in effect is that this velocity vector is going downwards, which means that this particle is going to take a curved path. The direction of the velocity is going to change. And note here that the force is normal to the velocity. So this angle is normal. So at all times, the force is normal to the velocity. Hence, this particle is going to move around in a circle. So this particle takes a circular path inside this magnetic field. See what's happening here? The particle has a velocity in this direction. The force therefore acts in the upward direction, and the change in the momentum is in the upward direction, so the particle starts moving upwards. So along this circular trajectory, all along the trajectory, the velocity vector is tangential, or the momentum vector is tangential all the time. And the force vectors are always pointing towards the center of this circle. And they're always normal to the velocity vectors. And as it should be, because F equals QV cross B, the force has to be normal to the velocity. If the velocity is along the tangent, the force is towards the center of the circle. This force actually gives you the centripetal force. So this particle actually takes a circular trajectory inside a magnetic field. Alright? Now if you have, say, a magnetic field that is pointing out of the plane of this. Suppose you have a magnetic field pointing like this, B, and you have an electron or a proton that is injected into this magnetic field. Of course it's going to take a circular trajectory like this, right? It's going to take a circular trajectory. So the velocity is upward, the force is into the plane of the blackboard, so the particle is going to move like this. And if this were an electron, the particle is going to move like this. So it's going to take a circular trajectory. Now I'm drawing the circular trajectory in a vertical plane. Now, in addition to this magnetic field, if you also impose an electric field, E, and if this were a positively charged particle, then the electric field will also impose its own force, and this positively charged particle will be drifting in the direction of the electric field. So eventually what you would have is a spiral motion of the positively charged particle. So just in the presence of a magnetic field you have vertical motion, if this is the disposition of the magnetic field. And on top of it, you're now applying an electric field. So what's going to happen is that this circular motion is going to persist. It's going to be always there because the magnetic field is on, but on top of it you've applied an electric field, and the electric field applies a force of its own in the direction of the electric field. So this particle is now going to undergo circular motion or helical motion. It's going to move around in a circle, but it's also going to drift in the direction of the electric field. So this is the combined action of electric and magnetic fields. You had a question?
Sir, the direction of vector will always be same as the direction of acceleration.
Yes.
So it would be inverse or in the direction of the
So the direction of the the direction of the acceleration is in the direction of the force. I'll draw a diagram to describe this in a minute, okay? One question, yes. यहाँ पे V cross will be upward ही है ना, ये force की direction. यहाँ पे V cross V downward है. V इस side पे है, B out of the plane है, downwards. All right. Now what I would like to show is what is the radius of this, what's the direction of the force, etc. What's the radius of this path, what's the time period of this motion. Of course it's periodic motion. It's not a pendulum, but it's circular motion and it's periodic. It happens with a certain time period. Now if I were to draw, let's draw a section of this circular path. I take a point here. The momentum vector is P1. At some other nearby point, the momentum vector is P2. And both of these vectors are tangential to the circle at those points, correct? And these are parallel to the velocities. The momentums are just the velocities, correct? Now this is the center of the circle. I draw this radius and I draw this radius. Of course these lengths are the same. Suppose this is a small angle, really small, delta theta. Alright? Now if I were to take this angle, this is going to be 90 degrees. This is going to be 90 degrees. So the angle between these radii is delta theta. What's the angle between P1 and P2? आप बताओ इम्तियाज? या आप हाँ ये क्या एंगल है इनके दरमियान? Sorry? The angle between these momentums is also going to be delta theta because each one of them is normal to a radius vector. Alright? So if I were to draw this diagram again, what I actually have achieved is a vector P1 and I can join their tails. This is vector P2 and this mutual angle is delta theta. Now if I connect these heads, I can draw another vector. This vector is P2 minus P1. So this vector is really delta P, the vector that I've drawn over here. Now if this delta theta is really small, then this is actually an arc. And this arc will be coincident with the vector. Because if delta theta is small, you can approximate this arc by a straight line. So the length of this arc is going to be the same as the length of the vector. Alright? So this delta P, the magnitude delta P is going to be roughly equal to this radius, which is just P1 or P2, I call it P, into delta theta. Alright? Now I divide both sides by delta T. Alright? And I take the limit that delta T is really small. Delta T is really small. Now this would imply that this thing turns out to be a rate of change of momentum. dP by dt, right? I put a vector sign on top of it. This is just a magnitude, so I call this magnitude of the vector P. And what is this? Delta theta over delta T. In the limit, the delta T is really small. What's this? Yeah, this is just omega. This is the angular velocity, omega. And it's a vector. And this is just, the rate of change of momentum is just the force that acts on this particle. Alright? So there are 2 points here. There is a force that acts on this particle which causes a change in the momentum. Okay? That force is changing the momentum, but it's not changing its magnitude. It's only changing the direction of the momentum vectors. So force can act in 2 ways. You can have dP over dt in 2 different ways. You can have a change in the momentum, the magnitude of the momentum without the vector sign in a particular direction, or you could have P times the change in the unit vector. So this is a change in the direction and this is a change in the speed. But the speed is not changing here, so this term is really 0. So what is really changing is the unit vector's direction. So now you have a force that is equal to P times omega. Now this force is actually given by the Lorentz force. So if I take the magnitudes here, the force is given by Q VB, right? This is the Lorentz force. The angle between the magnetic field and the velocity is normal. So sine of 90 is 0. So this is a force. You can equate this force to P, omega. Without the vector sign, I'm just dealing with magnitudes. So QVB equals P omega. Now if I were to do something else, I were to replace this omega by V over R. I can replace this omega by V over R because it's circular motion, and R is the radius of this trajectory. So I have a radius R and the particle is moving inside this circle inside the magnetic field. So I replace omega by V over R. I get P here is QVB. So this V just goes away. But this momentum has a V inside it because this momentum is a velocity. So if I replace this P by mv, and I would also like to put a gamma with it in order to account for the fact that these particles can be moving at really high speeds as they do in particle accelerators. So I have P equals gamma mv. So gamma mv over R equals QB. In other words, the radius of this trajectory is given by gamma mv over qb, and it depends upon the magnetic field, and it depends upon the charge to mass ratio, and it depends upon the speed with which the particle has been launched inside the magnetic field. and the speed does not change, only the velocity changes. So this defines what the radius of this object is. If I were to find out omega, which is given by v over r, as we know, which is just the angular frequency, and I take this v and I take this r is gamma m v q v, the v goes away, and omega is given by one over gamma charge to mass ratio q over m b. So by looking at the angular speed of these electrons, I can find out the charge to mass ratio of the particle. So if I have an unknown particle that goes into a cloud chamber, so I have this cloud chamber which has a gas inside, and an unknown particle actually comes in, and this particle is charged and it comes in with a velocity v. Its charge to mass ratio is q over m. Then this particle will undergo circular motion if I have imposed a magnetic field inside this chamber. And by looking at the radius of this circular trajectory, I can find out the charge to mass ratio of this particle. Alright? So this is what happens inside a cloud chamber. So pair production takes place whenever a photon decays into an electron and a positron. Alright? The electron and positron have equal masses, but they are opposite signs. So one of these will undergo a trajectory like this inside a cloud chamber, and the other particle will undergo a trajectory in the opposite direction with the same radius. Okay, because they have the same charge to mass ratios. So by looking at these tracks inside a cloud chamber, you can identify particles, because the particles are known by the charge to mass ratio. Now if I have this relationship, and if I were to modify this a little further, I can find out the time period of the circular motion of these particles. The time period will be given by 2 pi over omega. So this is simply 2 pi gamma m qv. Now does this time period depend upon the radius of the particle? It's totally independent of the radius of the particle. So if I have particles moving in a smaller trajectory, and then I have particles that are moving in a larger trajectory, the same particles with the same charge to mass ratio, then these time periods are going to be the same. Which means that in the larger orbits, the particles are going to move with higher speeds. And this is evident here. Larger the orbit, larger will be the linear speed for a given magnetic field and charge to mass ratio. So this radius is actually independent of this radius depends upon the speed, but the time period is independent of the radius. This is just like a pendulum. A pendulum with a longer length has the same time period as a pendulum with a shorter length. So now you have charged particles issued into a magnetic field. They are moving in circular trajectories. By the way, you haven't proposed an electric field, just pure magnetic fields will navigate, make the particles navigate in circular trajectories. You had a question over there. Speak up. Yes. So it's moving in a circular path. So in this particular case, let's find out the direction of the electric field, the net field. So the net field is here. If you did not apply electric field, the net field is downward here. The net field is into the plane, into the circle here, into the circle here, it's into the circle here. So this moves this particle going in a circular trajectory. Okay. Now on top of it, you've applied an electric field in this direction. So this is Fe at this point, and this is Fm. So what's going to happen is that the particle, no doubt, is going to move downward in the vertical plane, but at the same time is going to nudge in the forward direction. And the pitch of this screw will depend upon the relative magnitudes of the electric and the magnetic fields. If this electric field is large, it will move a long distance in the lateral direction before it has made a complete circular trajectory. So the pitch of this is just like a screw. The pitch of this screw, how many turns you make when you make a lateral advancement, depends upon the relative magnitude of the electric and the magnetic fields. Now I would like to show to you an important particle accelerator. And this concept is used in a particle accelerator of a special kind which is called a cyclotron. Alright? G. ये वाला ये एक force है ना, the rate of change of momentum. Now the momentum is a vector. It will have a magnitude and a unit vector. The unit vector specifies its direction. So the momentum can change in two ways. It can either change purely by change in momentum or by change in the unit vector. So this is really speed. This is tangential acceleration. Okay, acceleration along the tangent, but that's zero because there's no change in speed as the particle moves in a circular path. Now, a really interesting device is the cyclotron. It was discovered in 1929 in Berkeley. Now what happens is, in a cyclotron, we have two metallic hemispheres. And they are hollow from the inside. These are generally called Ds because of their shape. Now if you look at the side view of one of these Ds, okay, this is what the D looks like. And in the side view there is a slit, there is an opening here, and of course it's hollow from the inside. So there is an opening here. So a particle that is inside can actually move from one D to the other if it has the proper velocity. Alright? So now what happens, a small particle, say we have a positively charged particle, like a hydrogen nucleus, so proton, is made inside, it's ejected here, okay? It comes out from some bottle. We have a source of protons, like we can have source of electrons. Okay? We ionize hydrogen inside a glass bottle. The ionized hydrogen are just protons, right? Hydrogen can be ionized by applying an electric field or a potential of 13.6 volts. That's how you ionize hydrogen, right? ये तो चीजें आपको पता है ना? ठीक है? Hydrogen ionization potential आप पढ़ते हैं 13.6 electron volts. What does it mean? You apply a voltage of 13.6 volts, electrons will be knocked off from the hydrogen atom and you get protons and electrons. Now you can take protons, you can steer them with the help of electric fields because they are charged particles. So now you have issued a proton here and you would like to make this proton go to very high speeds because you would like to make one proton smash into another proton and give you new particles. That's what happens in the CERN reactor, in the LHC. You smash beams of protons at exceptionally high speeds at energies of 10 electron volts so that you get a zoo of new particles. And you hope that one of those particles is the Higgs boson. So you have to accelerate these protons to exceptionally high speeds. But you have a bottle of hydrogen, the speed that you will get is just half mv square will just be equal to kb times t, the temperature. It's really small speeds. So now you have this proton and you would like to accelerate it. Now what you would like to do, you would like to apply a voltage to these Ds. A positive voltage here and a negative voltage here, V0. You would apply a potential difference between these Ds. So what this proton would see is it would be accelerated across this gap and it will move towards the other D, towards the negatively charged D. Alright? Now this electric field, where does the electric field exist? Does it exist inside the Ds or only inside the gaps? आप तो ये electric field कहाँ exist करेगी? इधर exist करेगी? इधर भी करेगी? ये conductors हैं. There will be no electric field inside the Ds. It's a hollow conductor, there will be no electric field inside the Ds. but there's a potential difference. So this is just like a capacitor. There will no doubt exist an electric field in between, but there will be no electric field inside the Ds because it's a conductor. So E will be 0 here, E will be 0 here. This gap is really small, but still an electric field will exist inside this gap. So what will happen is that this proton will accelerate only inside the gap. Okay? And it will acquire a new energy. Its potential energy is going to decrease inside the gap, which means its kinetic energy is going to go up. जरा पानी ला देना भाईजान. जुल्फिकार पानी ला दे. So its potential energy is going to decrease. It's going towards a negatively charged plate. Its kinetic energy is going to go up. How much is the kinetic energy going to go up? It's going to go up by V naught into the charge on a proton, which is E. So it's going to take a slight kick in its energy. If this is 1 volt, the energy will go up by 1 electron volt. If this potential is 10 volts, the energy will go by 10 electron volt, which are small energies. And you would really like to go up to mega electron volts or giga electron volts or tera electron volts. You would need energies that are millions of times higher than this. So even though the proton has been accelerated, the acceleration is so small, the peak in energy, the boost in energy is really small. But this entire medium is placed inside a magnetic field. That magnetic field, suppose, is pointing out of the plane of the black hole. So we have magnetic fields pointing out of the plane of the black hole, right? Everywhere. It's a uniform magnetic field. I'm not drawing many of these circles because it was just going to clutter the diagram. But remember, there is a magnetic field that's pointing out of the plane of the black hole. Now what's going to happen is that inside this region, this particle is going to undergo a circular trajectory. So it's going to move with a certain radius. Okay? That radius, by the way, is given by this. It depends upon the charge to mass ratio of the proton and B, the magnetic field that you applied. And the speed inside this region remains constant. Nothing is going to happen to the speed because the magnetic field does not change the speed. However, if at this point it comes out into the gap again, it has to move against the electric field. This proton has to move uphill. Okay? Because now it's moving towards a positively charged plate. Now at this instant of time, you know what this, how much time does it take for the particle to come here? How much time does it take? Could anyone tell me the time that it takes for the particle to come back to this point? Suppose this gap is really small. If this is the time period, how much time does the particle take to come back here? It's half of this time. So if after time t by 2, after t by 2, what's going to happen is that I would like to switch this supply. Okay? I would like to make this positive and I would like to make this negative. So how do I switch supplies? I apply an AC voltage. So what, instead of applying a DC voltage, if I were to apply an AC voltage here, I just remove this sign here and replace it by an AC voltage. And this voltage V applied is given by some V naught, say sine omega t. If I were to have this omega, if this is the omega that I'm talking about, should I have an omega here? Yes. If this is my time axis, this is my applied field. At some point in time, I have a positive field, V naught. This is the time when this particle is issued. So a positive V naught is applied and this particle is accelerated towards the right t. So this is this point. After a time which is equal to t by 2, which is simply equal to 1 over 2, time is 2 pi over omega. where this omega is given by this. I have pi over omega, where omega is defined by QB gamma m. So this is my time period half. So if I have this time period half, which is precisely given by the relativistic correction, which is taken to be 1 for the time being, pi into the mass over the charge of the proton divided by the magnetic field that I have written. I know all of these parameters. If I adjust the voltage, the alternating voltage in this fashion, I make its frequency match the frequency omega, then at this point in time, the particle would have reached here. And the electric field is going to reverse its direction. And when it reverses direction, it takes an additional boost of energy. Right? And that boost of energy is an additional V0 E. So in one cycle, I get a boost of energy that is given by 2 V0 E. Now when this initial energy goes up, the kinetic energy goes up. Because you all know that V0 E is given by half mv squared. So an additional boost of energy gives an increase in the kinetic energy. What's kinetic energy? It's simply the velocity squared. So when this goes up by V0 E, the speed goes up. And when the speed goes up, when this goes up, the radius goes up. So what's going to happen now is that when the particle has taken an additional injection of energy from the electric field is boosting the energy. Then it enters this region where there is no electric field, but there is a magnetic field here. And now in the presence of this magnetic field, a new radius is produced. So in this new radius, so the particle comes here after taking an injection, a tonic of energy from the electric field, and it goes into a new trajectory with an increased radius. And now the AC voltage is still on, and it's switching in a direction at a time which is synchronized with the angular speed. The angular speed, by the way, does not depend upon the radius. So you can keep on increasing the radius, the angular speed remains constant. So the time period remains constant. So this AC voltage has to have a fixed frequency, but only up to a certain limit. I'll explain that. So when this reaches here, the magnetic field once again reverses, the electric field once again reverses its direction because of the applied AC voltage. And now what's going to happen is that an additional boost of energy is acquired by the protons. And now they start moving with bigger and bigger radii. And they keep on picking up energy. And eventually, this proton can acquire really high speeds, up to the order of mega electron volts or giga electron volts, by just these small peaks in energy. Alright, and the radius keeps on increasing. However, this is how you put protons into exceptionally high speed, because you cannot apply a voltage that is mega volts. It's not easy to apply sustained voltages of the order of mega volts. Here you just have, say, a few volts and with an AC voltage at the proper frequency, you can make the electrons actually go to really high speeds by giving them small boosts of energy, small injections of energy. And this is how a cyclotron works. Remember, however, there is one caveat. This omega, if you notice here, also depends upon gamma. So when the speed goes up, this factor really goes up. When this factor goes up, and the radius, because the speed is actually going up, the radius is no longer independent of omega. You see, the omega would now depend upon the speed. So the speed goes up, omega changes. We've assumed that at low speeds, which are non-relativistic speed, this is 1, so this does not really exist. But when you've accelerated the electron to speeds close to the speed of light, in CERN, the speed of protons is roughly 99.999% of the speed of light. It's really high speeds. Okay? So there gamma cannot be ignored. So when gamma goes up, the angular speed goes down. When the angular speed goes down, the time period goes up. So this AC voltage has to be adjusted in such a way with the passage of time so that it is synchronized with the angular speed. And if it's difficult to adjust the frequency of this, so if this goes up, omega should actually go down, correct? In order to keep everything constant. So one possibility is that you start off with a high frequency, but as the speed goes on increasing, the frequency of this applied voltage goes down. Now I'm drawing an exaggerated diagram, but this is the kind of signal that you would like to apply. But it is difficult to apply. You can actually keep this constant, but you can vary this. This magnetic field can be ramped down with the passage of time, so that everything matches and everything is synchronized, and you have something that is properly under your control. Half a minute of silence, and then we move on with some really interesting ideas. Now I would like to talk about something really interesting. We've seen forces acting on moving particles, charged particles. We've seen forces on current carrying conductors. What are the forces on dipoles? Because the magnet is a dipole, how does a force act on a dipole? How is a magnet attracted to another magnet, for example? So now I would like to talk about forces on dipoles. And with it, I would like to talk about torques on dipoles. In fact, this is how you get electricity here. This is a torque that acts on a dipole inside an electric generator that produces electricity. Now what is a dipole? A dipole is just modeled by a circulating current. So I have a circulating current, like a moving charge, an electron moving in an orbit, right? Or a real current loop. Okay? Now this produces a magnetic field. The direction of this magnetic field is normal to the plane of this loop. It's denoted by mu, and is given by the current I times the area vector. The area vector is just normal to the plane of the loop. Remember, this loop can be circular, this loop can have an arbitrary shape. Okay? So in this case, I can still define a magnetic moment mu. It's given by I times A. Now this magnetic moment, it's a dipole. Okay, it will produce a field. We know that field drops off as 1 over r cube. Now suppose that I place this magnetic dipole inside a magnetic field. Okay? Now this current carrying loop is inside another magnetic field that has been synthesized somehow. So let me draw a fresh diagram. This is the magnetic moment mu. And now it's placed inside a uniform magnetic field, like this, B. Remember, this is a uniform field, that's why I've drawn equally spaced magnetic field lines. Now I would like to find out the force that acts on this dipole, or on this current carrying loop. Suppose it's in a circuit, it's a rigid wire. Now if the current is going into the plane of the blackboard here, then IL cross B, the force points in this direction here, on this section of the wire. On this section of the wire, the force is going to point in this direction. This is F1, this is F2. Here, let's look at the force. Current, magnetic field, the force is pointing out. So the force here is pointing out of the plane of the blackboard, right? Outwards, F3. Here the force is going to point into the plane of the blackboard. So if this is a rigid circuit, it cannot move. If it's a rigid circuit, then nothing is going to happen to the circuit. The net force on this circuit is always zero. Okay, because if you take the vector sum of all of these forces, it's going to be zero. Correct? However, if this were an elastic circuit, a flexible circuit, and I'll give you some problems in the quizzes or tutorials, like if this were an elastic circuit, what's going to happen is that this band, this circuit can actually expand or dilate a little bit. It can breathe, it can go out. Okay? If the magnetic field were in the opposite direction, you could have the inverse effect. This circuit would actually shrink. And you learn that when it shrinks, okay, so it shrinks. But this is a uniform magnetic field. Okay? Now if I have this same current carrying loop, and this is my mu. Okay, which means that this is my current. Now still I have a uniform magnetic field, but that magnetic field is pointing like this. And it's a uniform field, still uniform, such that the angle between the magnetic field and this plane is always theta. Still I have my dipole immersed in a uniform magnetic field. It could be slanted, but that doesn't matter. Now if you calculate the forces once again, let me do this for two particular. Now, I current going into the plane of the blackboard, B pointing upward, so there's a force that is acting like this. So how do you draw the forces here? It's nice to draw a plane. Right, now this is a slanted plane. Now in this slanted plane, let me draw this plane again here in a zoomed in fashion. Now this is slanted. This makes an angle theta with the horizontal. Inside this plane, the magnetic field is like this, B, and IDL is into the plane, so it's like this. IDL is like this. IDL. So of course the force has to be normal to this plane. So IDL cross B gives me a force in the downward direction. So the force in this case is pointing in the downward direction. This is F1. So the force on this section is pointing downwards. Here the force, if you draw a similar construction here and draw a plane like this, the force is going to point upward. So if you can repeat this process for all sections on the wire, and the net force once again will turn out to be zero. The net force on this section is zero. The net force on this dipole is zero. So whenever you have uniform magnetic field, the net force on dipoles turns out to be zero. Alright, so far so good. But zero forces does not necessarily mean zero torque. Suppose I have a dipole, and for convenience now I'm going to make a rectangular dipole. G.
How is this through a dipole?
Any circulating current will produce a magnetic field that resembles a dipole. Okay, that I explained in the previous class. It's called a dipole, right? Now what I would like to do, I would like to draw a dipole which is, say, rectangular. This is the length of this dipole, this is the width, and it's carrying a current. Now what's the direction of the magnetic moment? अब इसका मैग्नेटिक मोमेंट म्यू की क्या डायरेक्शन होगी अगर ये करंट की डायरेक्शन है? आप बताएं कि perpendicular to what? To the plane, into the plane or out of the plane? Into the plane होगी. 50% statistics काम नहीं की यहाँ पे. देखो अब अपने right hand की fingers को rotate करें in the direction of the current, the magnetic moment is into the plane, right? So the magnetic moment is pointing in. This is the direction of the magnetic moment, right? Okay. Magnetic moment is in. Now suppose I apply a magnetic field. Okay? And that magnetic field is, say, in this direction, B. And it's a uniform magnetic field. The net force on this dipole is still going to be zero. And if it's rigid, it will undergo no acceleration. The net force on this side is zero, on this side is non-positive, and this side is non-zero, but they will be in opposite directions. The forces here will cancel out. There will be no force on this section, no force on this section. So the net force on this dipole immersed in a uniform magnetic field is still zero. However, let's look at the force on this section. IL cross with B. The force is into the plane of the blackboard. Okay? So here this section experiences a force into the plane of the blackboard. So this is the direction of force F1 on this section. Here there is no force because the current is parallel to the magnetic field. There is no force here. We ignore these tether ropes. We ignore these lines. Okay? Now on this section, the current is going downward. So the force is now pointing out to the plane of the blackboard. So here the force is pointing out, 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 out. On all of these sections, it's out. So now what you have, a force pointing in and a force pointing out. And if this, even though it's a rigid object, it cannot explode, it cannot disintegrate, it cannot change its shape. But if this object were free to rotate about an axle here, then it can actually twist. So this side goes in, this side goes out. So it's going to twist. This side, so if this is the coil, this side goes in, this side goes out, so I'm going to twist. In the presence of this uniform magnetic field, even though the net force is zero. The net force is zero, it's going to twist. So there's going to be torque that is acting on this object. And how much is that torque? Torque is denoted by tau. And I'm going to talk about its magnitude first. The force here is F. This force is the same as this force. Because the length is the same and the field is uniform, by the way. So how much is this force? It's I. The length of this section is LB. Alright? This is the force on this section. But for the torque you have to multiply it with the moment arm. That moment arm is W over 2. But this is the force into the moment arm of this. This is the force into the moment arm of this. Both of them twist the coil in the same direction. So their torques will be additive. So you have this force into moment arm plus this force into moment arm. You multiply this with 2 to get I L omega into B. If I is a current, let's denote it with small I for consistency. So this is the torque that is acting on this dipole. Now what is L omega? What's L omega? It's the area of this dipole. So current times the area of the dipole is just the magnetic moment, mu b. So the torque equals mu b. And what's the direction of this torque? If I were to replace all of this by vectors, because the magnetic field could be pointing in opposite direction, this magnetic moment initially could point in any direction whatsoever. I can make this into a vector equation, and that vector equation will be my tau equals mu crossed with b. If you observe here, mu is pointing out, b is pointing in this direction, mu is pointing in, torque is pointing in the downward direction. Downward direction means that the curl of the fingers is in the direction of the twist. So this coil will twist like this. If you look at it from the top, this coil, looked at it from the top, this is W. This coil is going to twist like this in the clockwise fashion from the top, as seen from the top. And it's going to accelerate because there is a torque. This torque will produce an acceleration which is given by the moment of inertia times the angular acceleration. Newton's laws of motion will now take over and will define the mechanical motion of this object. It can act as a simple harmonic oscillator, right? So once this coil twists, its magnetic moment, of course, is going to twist. So it might come a stage when this coil has twisted in a fashion. So this is the initial position of the coil. The moment is pointing in. And the magnetic field is like this. So the angle between the magnetic moment and the magnetic field is 90 degrees. But then it's going to twist. If this side is A, B, C, D, a time will come when it has twisted in such a fashion because of the application of the torque that you get a situation like this. Because it has twisted, it has gone around. This point is B, this point is A, this point is C, this point is D. And the current is still flowing in the same direction. And the magnetic field is not changed. Since the magnetic field is not changed, this is B. Now what's the direction of the magnetic moment? Could you point out the direction of the moment? It's parallel to the field, mu. Now what is the torque? It's 0. Because mu cross B is 0 here. So the torque is not constant, it depends upon the relative angle between the magnetic moment and the magnetic field. So here the torque is maximum, here the torque is minimum. And the variation of the torque goes as sine theta, as the angle between mu and B. Now something really interesting pops up. If I have a magnetic moment, this is my magnetic moment, mu, and this is placed inside a magnetic field. Suppose this is my direction of a magnetic field, B. Now this magnetic moment, just as a charge that is placed inside an electric field has an electric potential energy. Correct? Now you have a circulating charge, which is a dipole. Remember, in magnetism you don't have magnetic charges or monopoles. A circulating current or a dipole takes the role of a charge in magnetism. So now this magnetic field, the magnetic moment, is placed inside the magnetic field. This moment will have some energy, some potential energy. Okay? Now you can have a situation like this, in which the dipole is parallel to the magnetic field. And you can always visualize this dipole at the back of your heads without compromising your mathematical and intellectual rigor. You can imagine that this dipole is a tiny magnet, in fact. Which this is the north pole, this is the south pole. This is just a figment of your imagination. Remember, there are no north poles and south poles in real magnet, because the concept of magnetic monopoles does not exist. But at the back of your imagination, for a minute you can assume that this is the case. And of course this happens. If this is the magnetic field, this means, for example, if this is the earth, This means that this is the Earth's north pole, right? So it's producing a magnetic field like this, and this is the direction in which a magnetic compass needle will actually orient itself. So this is indeed a good condition, which means it's an energetically favorable condition. This condition will have lower potential energy, in other words. Okay? A magnetic compass will tend to align itself in a particular direction, which means it will tend to lower its energy. So this magnetic dipole inside a magnetic field must have some energy associated with it. If you have the converse situation in which this is the magnetic field, but your magnetic moment is actually pointing in the opposite direction. So this is your magnetic moment now, mu. This tends to be a high energy configuration. Okay? Low energy, high energy. But your magnetic moment can actually be pointing in any direction whatsoever, right? These moments could point anywhere. For each configuration, there is a magnetic potential energy. That magnetic potential energy, if you look at these extreme cases, turns out to be equal to U equals to minus mu dotted with B. The magnetic moment's dot product with the magnetic field. Okay? If mu and B are parallel, this is cosine of theta is 0. This is a negative number, so the energy is lower. Negative energies are lower. If these are anti-parallel, like this configuration, the energy will be higher because this will in turn be negative. So a negative of a negative is a positive number. So this is a high energy configuration, high U. This is a low U configuration. Now I would like to stop here. In the next lecture, I'm going to see how this magnetic potential energy causes two magnets to attract one another. Alright? And then in the next lecture, I'm going to talk about magnetic materials, ferromagnets in particular. So please submit your homework in time. I'm going to upload the tutorials for this week. Last week you haven't been very attentive with the tutorials, so you have to do double up your work this week. Alright? Inshallah, see you on Thursday. Thanks a lot.